So you can now type in your attendances, and we will start today's class. So you have to type your name followed by the statement that you are present. All right. So today we will start with something called the marginalization. These are in continuation of the general properties of different distributions. So, in the last class, we introduced this distribution that contained more than one random variable. So we call those kind of distributions as joint PDF. So suppose the joint PDF, uh, if xy is known, okay, and then one might be interested to know. So this fxy gives you the probability that x and y simultaneously belongs to a given interval. So this thing actually gives you the probability that x belongs to x plus dx, uh, and this is the most important thing, and y belongs to y y plus dy. Okay, so actually not this, but fxy uh, fxy dx dy. This one gives you these probabilities. Now, I might be interested in knowing what is the probability that x will be in the interval x to x plus dx, and it doesn't matter where y belongs. Okay, so suppose for some reason I am interested in that the probability of x belonging to this interval x to x plus dx, no matter where y is. Okay, so I don't care about y anymore, and I want to only know that probability of x only. And I so the thing is then I have to integrate the possible values of y. So I notice that the probability that x belonging to x plus dx and y belonging to y plus dy is this. So if I am only interested in probability of x belonging to x plus dx, then I write that thing as fx x dx. So this is kind of another distribution for x, and that will be equal to f xy dx dy. And since I am no longer interested in where y is, so this was the probability of y belonging to y plus dy, y to y plus dy. So if I integrate it over the whole range of y, so if I do the y integration, so y equals minus infinity to plus infinity, then this is the probability of x belonging to x to x plus dx, and y can be anywhere between minus infinity to plus infinity. So that is the probability, that is the required probability that we have. Okay, and so this then will be called this fx x, this thing is called the marginalized PDF of x. So this is called the marginalized PDF of x because I don't care anymore where y is. Okay. Now, uh, you might be also be interested to find out what is the probability of so what is the what is the generalization of the concept of conditional probability here in the case of continuous distribution. So instead of asking what is the probability of x belonging to x sorry what I was saying. So instead of asking what is the probability of x belonging to x plus dx, provided y can belong anywhere, let me now ask the probability. So I ask the probability of y belonging to, sorry, so y belonging to y plus dy given say x equals x0. So I have given a particular value of x. So x has taken a value. I call it x naught. And if x takes the value x naught, then what is the probability that y will be in this particular region? Okay, and that thing I will denote it by the conditional PDF of y given x equals x0. Okay, so y given x has a particular value, and then how to find that? So how to find this conditional PDF? Okay, uh, it's easy if I remember my basic assumption about conditional probability. So you remember the fourth axiom of Kolmogorov. This gives me that the probability of B given A, okay, is given as P of A intersection B, that is A and B simultaneously happening, divided by probability of total probability of A happening. Now, in terms of probabilities, if I want to compare, so this P given A, let us compare it. Okay, so this P given A. So I want to understand that what is the probability of to find y between y to y plus dy. So I compare B with y, okay? And A is given, so I compare A I compare with x0. Okay. So on the left hand side there is a probability. So let me write down a probability. So this will be on the left hand side, this will be h of y given x0. Okay, and the times dy, because this is the probability h of y times x0 times dy. This is the PDF. The h is the PDF, and times dy is the probability. This equals to, okay, P of A and B happening, the probability of A and B happening simultaneously. That means probability that x will be x0 and y will be between y to y plus dy. Probability of that happening. How much is that? So that will be given by f of x0 y times dy dx. So here this dx means that x is in the neighborhood of x0, not exactly at x0. That is I take by dx, and divided by probability of a, and a is x0. Okay, so total probability of uh, a happening. That means total probability that x will be around x0, no matter where y is. Okay, so that will be given by, so the denominator is given by just the marginalized distribution of x evaluated at x0 times dx, because that is the probability of finding x in a certain neighborhood, no matter where y is. Okay, so that is my denominator. So if I cancel these two dx's, then and if I also remove this dy with this dy, then I get the relation between the marginalized PDFs. So the the conditional PDF of y given a value of x0 equals to the joint PDF, that is x0 y, divided by the marginalized PDF of x0. Okay. So this is the relation. If I need to find out conditional PDF, then we need to use this kind of relation when applying to a continuous distribution, the case of a continuous distribution. Okay. Now, before I move on to examples of specific distributions, let me mention some more properties of a distribution. So far as our discussion goes, uh, what we have is that, so suppose I have a probability distribution that look like this, suppose, and suppose you have calculated the mean, and the mean is here. So this is your mu, suppose, okay? And this is your x-axis, and this is your fx. This is mu, and this mu sometimes does not give you the full picture of the distribution, like what are the typical properties of the distribution. That's why we hello, is anyone saying something? Okay. That's why we use sometimes other things called the median and the mode. So the mode is simply the point where the distribution function is the maximum. So for this example, this will be the my mode. So this the value of x for which the PDF is maximum, kind of the most likely value in a way. The most likely value of x is kind of called the mode. Okay, and then there is this thing called median. So median will be the midpoint of a distribution, meaning that the area on the right and the area on the left from that point are equal. Okay, that means suppose if you draw another line here, so if you say x equals this point is the my median, that means the probability of finding x values that are greater than this red line is exactly the same as the probability of finding values of x that are lower than this thing. Okay, so so then this red line is kind of the midway between these two probabilities. That is exactly the midpoint. So from this point, you are equally likely to get values greater than that or less than that. So this point is called the median. Okay, so this line basically. So this is the definition of my median of a distribution. And sometimes these terminologies might come in handy. So it's better to declare them in the beginning. What we mean by that? What we mean by these things? Now. Then we move on to some examples of some distribution. So let me do examples. The first example that is kind of given in any textbook or any book of this statistical distribution is the binomial distribution. The first we discuss binomial distribution. So to before we talk about binomial distribution, uh, we need to discuss something called the Bernoullian trials. So let me first define something called the Bernoullian trials. So, so a series of trials is said to be uh, Bernoullian if number one, the trials are independent. Number two, uh, every trial has two possible outcomes. Let me call them success and failure. Okay. And the thing is that uh, the success probability is constant for all the trials. Okay, so I will call this success probability, I will denote by the alphabet P. So just note what are Bernoullian trials. So you can, if you want some context, you can think about again coin tossing and die throwing. So the trials would be independent. So basically, suppose you are tossing a coins many times, say 50 times. So each of these 50 tosses are independent of each other. The outcome of the second toss will not depend on the outcome of the first toss. So these are independent trials. Okay, no trial influences other ones, and the trials have each of the trial has two possible outcome and only two. I have denoted it success and failure, but it can be say heads and tails for coin tossing, and say for dice throwing it can be getting either even or odd, or getting a two or not getting a two. Okay, this can also be like you have to define two possible outcomes for that, for those trials, and you are good to go. And the success probability is constant for all the trials. Okay, so if your coin is fair, then every time you are tossing, the probability of success remains constant, which is 50%. So it is constant for all the trials, and then you keep on tossing. And then I define the random variable that is under consideration is, suppose this x is the random variable that denotes the number of successes. So this denotes the number of successes, okay, in in Bernoullian trials. Okay. Uh, then the distribution, if I denote it by fx, that means this means the probability that we get x number of successes in trials. Okay. So and then this is basically given by the probability that the value of the random variable is x. So this x equals to x, and so remember I will have x successes. So how many ways I can have x successes. uh, so I have to choose x entries out of n entries, and the number of ways I can do that is ncx. So I can choose in this number of ways that how many that I will have x successes. So I have chosen x entries out of small n entries that are candidates for my success, and I have to multiply that by the probability of success, probability of having x successes. The probability of having each success is small p. Then probability of having x success is p to the power x. Okay, because if the trials are independent and the probability is multiplied, again go back to the assumption of a probability. Then I also need to have exactly n minus x failures. For that, the probability of failure is clearly 1 minus p, and the number of failure is n minus x, so that is n minus x. Okay, so and this is true for n equals 0 to n. Of course, n cannot be greater than n. Sorry, x equals. Of course, x cannot be greater than n because I have total number of trials equals to n. So this is my definition of the binomial distribution. So this distribution is called the binomial distribution simply because this looks like the nth term in a binomial expansion of p plus 1 minus p. Okay. So first of all, let us check that this is indeed a probability distribution. So for a probability distribution to be a valid one, so you have to check that for all values of x, so x equals to 0 to n fx. Okay, so this should be equals to 1. So so the total probability should be 1. So this should be satisfied, and it is easy to check that, right? So if you take the sum of this, so if you now take the sum of this, then that gives you the binomial of p plus 1 minus p whole to the power n. So this thing is basically uh, p plus 1 minus p whole to the power n. So if you sum it, so if you substitute it here, uh, then you get p plus 1 of 1 minus p whole to the power n, and that is basically 1. So this is justified being called a binomial distribution. Okay. Now, first of all, then we are interested in finding the mean and the other properties of binomial distribution. So first, let me find out the mean. Okay. So so the mean of the distribution is given by, so this is the expectation value of x, and that will be given by summation over x equals 0 to infinity and x times x. Okay. So I noticed that since fx is finite for all values of x, the first term for x equals to 0 vanishes. For x equals to 0, the first term vanishes. So this sum essentially starts from 1. So if I remove 0 and I start the sum from x equals to 1 to infinity, that's fine. Okay. And then if I now plug things explicitly, so x equals to 1 to, sorry, not infinity. Why did I put infinity? X equals to 1 to n. Okay. So x equals 1 to n, x times fx is ncx. Let me write it down explicitly. So that's factorial n divided by factorial x times factorial n minus x. Okay. Then I have p to the power x, and just for brevity of notation, I use the notation q. Q is the failure probability, q n minus x. Just remember that this q is basically 1 minus p. Okay, it's nothing. That's it. Now, so let me first rearrange the terms a bit. So if I cancel this one with this one, I get factorial of x minus 1. Okay. And I rewrite factorial n as n times n minus 1 factorial. I rewrite factorial n minus x as n minus 1 minus x minus 1 factorial of the whole thing. Okay. And then this p to the power x I rewrite as p times p to the power x minus 1. Now I will take some things outside. So I will first take, let me mark it. I will take this n outside and this p outside of this summation, and I will write the rest. So notice carefully. So I am writing n times p, then x equals 1 to n. On top I have factorial n minus 1 because I have taken out n, divided by factorial x minus 1, and then again n minus 1 times minus x minus 1 factorial. Okay. I have p to the power x minus 1 times q to the power, I write it in a fancy way, n minus 1 minus x minus 1 is the same as n minus x. Okay. So now let me do some change of variables. So the change of variables look like this. So I define x prime as x minus 1 and say n prime, that is n minus 1. So in light of this, this equation will become n times p summation over. So if x prime equals x minus 1 and then if x starts from 1, then x prime will start from 0 and it will go up to n minus 1, so which is n prime according to my redefinition. And this one, n minus 1 factorial, is just n prime factorial divided by x prime factorial, again n prime minus x prime factorial, and then p to the power x prime, then q to the power n prime minus x prime. So the term under the summation is again a binomial expansion. So this one is again a binomial expansion. It's p plus q whole to the power n prime. Now p plus q is again 1, so this is 1. So I have obtained that the expectation value of x is n times p, which is not really surprising because p is the success probability and n is the total number of trials. So what do you expect? You will expect n times p number of successes. So no big deal in there. Now, in the same way, you might want to calculate the variance. Okay, so I will leave that as a homework actually, and I will give you some hint of how to do that. So if you now want to calculate the variance of the distribution, so the variance will be given by expectation value of x squared minus expectation value of x whole square. Okay. Now this x square, you write it in a fancy way for doing this particular exercise. So expectation value of x times x minus 1 plus x. So this is x square again, minus expectation value of x whole square. So you break it into two parts. So expectation value of x times x minus 1 plus expectation value of x. So this breaks down into two parts, like one is here and one is here, and minus again whole square. So now you notice that you know these two things. So you know this is equals n times p, and this one is equals n square p square, because expectation value of x you have found out to be n times p. Now this you have to find out, and you can find out in the same way as I have found out, mean the same trick. Instead of x here now should be x times x minus 1, and you will see that the first two terms vanishes, and then you have to again rename and do things. And if you do things correctly, you will find it to be n into n minus 1 times p square. Now, if you arrange them together, then you will get the variance that I will denote by v of x. If you rearrange this term, this will come out to be np times 1 minus p. Okay? Or basically sometimes written as npq, because q is my failure probability. You can check that this can be rearranged into even a more convenient form. This is n by 4 uh, minus of n times p minus half whole square. So you notice that the maximum value of the variance, so since the second term is, so this whole square is always positive, the variance is maximum when this one is minimum. So Vx equals to maximum. That is, the value is of course n by 4 when p equals half. Okay, and Vx is minimum equals 0 when p is either 0 or 1. So you see the variance is maximum, then the value is n by 4 when the p is equals to half, and it's minimum when p is equals to 0 or 1. Now this is also easy to understand. So if you remember, what does the variance gives us, it gives me how wide the distribution is, or how scattered your measurements are, or like how scattered your data is. So if p equals 0 or 1, that means you are having either total failure or total success. Okay. So in terms of coin tossing, if the coin is biased, let's say it's completely biased, okay, then you either get always heads or you get always tail. Okay. So there is no ambiguity in the value of x. Okay. You always get either head or always get tails. Now from the last classes, what we have learned is that if you always get a fixed measurement, this is fixed data, one data only, and that then the distribution looks like a delta function, and you have the variance equals 0, and that is what you are seeing, that for total success or total failure, the variance is 0, as I expect. When I will expect the variance to be maximum, when the data is scattered all over, okay, to the maximum extent. And when is that possible? If the coin is unbiased, if the probability of success or failure is equal, then you will get as many times of success and as many times of failure, and your data will be like spread the most when you have equal weightage to success and failures. And in that case, the spread of your distribution will be maximum, and your variance in that case is just n over 4. Okay, I will ask you to draw the binomial distribution using computers for different values of n and different values of p, to get a feeling that how this distribution behaves for different values of n and different values of p. How does p affects the distribution, and how does n affect the distribution? Okay, and that will be very helpful in understanding what I'm going to talk in the next. So the homework is basically plot fx as so parametrically, plot fx parametrically for different values of n and t, and see how things look. Try to get a feeling for the distributions themselves. Uh, by the way, a bit notational digression. So suppose here I have written fx. For future reference, I should write it as actually I will write, I should consistently write it as fx np. So whatever is on the right hand side of the semicolon are the parameters that controls the distribution, and whatever is on the left hand side of the semicolon are the random variables. Okay, so the distribution is on this random variable x and with parametric dependence on n and p. Okay, so I should write the binomial distribution in this form actually to uh, make these distinctions clear. Okay, so anyway, now let me move on to the next all important distribution. It's called, why did I do that? Yeah, here, let me put it here. So, the Poisson distribution. Again, this is also a distribution for discrete random variables. So the discrete random variables. So this the Poisson distribution. So let me write down. So random variable x is said to follow the Poisson distribution if uh, so Poisson distribution it's a parameter with parameter. This parameter I will denote by nu. Okay. If the PDF is given by this. So f of x with nu as the parametric dependence, it is given by nu to the power x divided by factorial x and e to the power minus nu. Okay, so this kind of looks weird if you don't know what I am talking about in this thing. Why people will think about a distribution like this. So the homework will be also plot this distribution for different values of nu. Okay, so homework plot this for different values of nu. By the way, here the values of x I did not mention, but here x can take values for x equals 0, 1, 2, blah, 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 up to infinity. So it can take values up to infinity, not a problem. So then just to check that it is really a distribution, so I first let's run the check for a valid probability distribution. So suppose now I do this sum, so x equals to 0 to infinity. Now x is 0 to infinity to be fair. So f x nu, and that will be given by, then e to the power minus nu is kind of a constant factor, so it comes out of the summation. Then sum over x equals 0 to infinity, nu to the power x over factorial x. Now, the thing under the summation is, again, if you notice, this is the definition of exponential. This is e to the power nu. Now, this e to the power nu and e to the power minus nu powers cancel, and you get e to the power 0. So this is e to the power 0, and that's 1. Okay. So the total probability is 1 as expected. So that is kind of relaxing, that we know that this is, I can call it without any fear that this is a valid uh, distribution, probability distribution. Now, again, I leave these as homework to check mm, that if you calculate the expectation values, so expectation value of x for this distribution, in the same way we did the binomial distribution, we can do the Poisson distribution also. So, in the first case, the sum is from x equals 0 to infinity, and then x fx nu. And so the sum will essentially start from x equals to 1, because again, uh, the first term is 0. For x equals to 0, the first term is 0. Okay. And if you do this thing, you will get nu NCL. Okay. And if you similarly, if you calculate the variance, okay, following the same trick as in the binomial distribution. So the variance, if you remember, expectation value of x times x minus 1, okay, plus expectation value of x minus expectation value of x whole square. Okay, so you have already found out this to be nu and this one to be nu square. And if you play your cards correctly and you calculate this thing, then this you will again find as nu square. So this one and this one will cancel out, and you will be left with Vx equals nu again. Now Vx, I sometimes define it as sigma square because it's the standard deviation. So the standard deviation is square root of nu. Okay, and so this is the so this has a very definite implication in physics lessons. So this kind of gives you why we take many measurements and why the size of data matters, and we have a more precise measurement if we have enough data. Okay, the uh, the understanding is that this Poisson distribution, this weird form that I have written down here, is not an accident. It's a limiting case of the binomial distribution. Okay? So let me put it down. So Poisson distribution is a limiting case of the binomial distribution. Okay. To see this explicitly, and the limit basically is the limit that I am talking about in this limiting case is that the number of trials is very large, so n tends to infinity. The success probability is very low, p tends to 0, but their product np is finite. Okay. So this is the limiting case in which your binomial distribution approaches the Poisson distribution. Okay. So let me try to show you how that is, and it's not a mathematically challenging proof to do. It's fairly simple, I would say. So the binomial distribution, if I write clearly, so the binomial distribution in terms of the parameter n and p, these read n c x times p to the power x 1 minus p whole to the power n minus x. Okay. And if you break down n c x, then ncx is n into n minus 1 up to x term. So the last term will be n minus x plus 1. So this is the term that is useful for me, divided by factorial x, okay? P to the power x, and then 1 minus p to the power n minus x. Okay. Now, let me do a few things here. First of all, there are x terms, right? So this one, this one, this one, these are x terms containing that. So if I take n as a factor out from each of these terms, so I take out n and say put it here, another n from here and from here also. Then notice carefully what I am doing. So I have taken a factor of n out, 1. In from the second one, I have then 1 minus 1 by n. Then dot 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 from this one also. Let me write down the second term also. 1 minus 2 by n. Dot dot dot. To 1 minus x minus 1 over n. Okay. So then I have taken out x number of n's from this factor. So I will have n to the power x. And I already had p to the power x. P to the power x. Okay. And this one divided by factorial x. Okay. And this term 1 minus p to the power n minus x, this is 1 minus p, according to my definition, is nu over n, okay, whole to the power n minus x. So let me put n upwards, and then I will put 1 minus nu over n whole to the power x. That's my 1 minus p to the power n minus x. Okay. I wrote it in a fancy way. Now n times p is nu, so this is my nu to the power x. Okay. Now I have to, so I only see n here. I only see n in this thing. So I have to evaluate this. I have to evaluate this whole thing in the limit n tends to infinity. Now let us do term by term. Let us see what we are left. So this nu to the power x and factorial x, they are not affected. So nu to the power x over factorial x comes out. Okay. Now for n tends to infinity, you will see each of this factor is 0. Okay. Sorry, not 0, it's 1. These factors are, each of them are 1, because it's 1 minus 1 to the power n. So this is basically 1. This product is 1, so forget about that. This one is also 1, because see, nu by n is approximately equals to 0, and 1 minus 0 whole to the power finite. So this x is finite, remember. Okay, this small x is finite in general. So the denominator is 1. So this denominator is 1. And now this is from your class 2 level calculus limit. If you take n tends to infinity and if you evaluate this, then you get e to the power minus nu. Okay. So if you have a plus sign here, that is the formula for e to the power x for n tends to infinity. So then this gives you e to the power minus nu, and I already have nu to the power x times factorial x. So the distribution is this times e to the power minus nu, which is precisely the Poisson distribution. So this is the Poisson distribution with nu as a parameter. Now you will ask, so what? So in a limiting case of binomial distribution, I get the Poisson distribution. The reason being is that this limiting case of this binomial distribution is kind of ubiquitous in physics. For example, you are looking at a radioactive decay. Okay. Suppose the radioactive decay of a material. Okay. So radioactive decay of a material. Then you have kind of, if you take a chunk of radioactive material, then there are kind of, say, of the order of 10 to the power 23 atoms, and you ask the questions how many will decay within an interval of 2 minutes. The probability for an individual atom to decay is really, really small. Okay, for an individual atom. You know, from 10 to the power 23 atoms, some of them will decay, of course, but the decaying of an individual atom is really small. Okay, so you get so since this is the number of atoms, so you get n large, n to be very large, and you also get p to be very small. Okay. But this n times p, this n times p is kind of fair, is fairly finite, and that is kind of the inverse of the decay lifetime. That gives you the probability of some of them to decay within a given time interval. So this is finite. So the ideal scenario is that in the case of this binomial distribution is the radioactive decay. Okay. And for radioactive decay, you see that these conditions hold, and Poisson distribution is perfectly applicable in case of this radioactive decay. And we do not have the setup for radioactive decay in our MSc in the laboratory, but it's a really nice experiment uh, uh, if you do the experiments of this alpha decay and beta decay, especially alpha decay, actually, we did this in our master's courses, and you will see that they kind of perfectly follow a Poisson distribution. And from that distribution, you can get the lifetime of alpha decaying nucleus, for example, and this is a really nice thing to do. So this is what we see also in experiment, that it observes that. Now, remember this we have found that this nu is the parameter and nu is the average. So this since this nu is the expectation value, then the expectation value is kind of the average. So this means this value of nu gives you the average number of decay in a given time. Okay, so the this is gives you the average number of decay in a given time, that I call the average count. Okay, so that's average count. And of course it's the average count, right? Because if you do the experiment today, you will get, say, nu equals 20. If you do it tomorrow, you will get, say, nu equals another number. Okay, it will never be the same. Okay, so you get many different numbers, so there is an error in that, and that error is square root of that count. Okay, so the relative error, if you say the relative error in that count is the error in the count divided by the number of count. Hold on a second. All right. So I'm back. So the relative error basically scales as 1 by square root of nu. So the more is the number of count, the less is your error, and that's why in a counting experiment, if your number of counts is high, you say that the relative error is proportionately smaller, and this tells you in why you should take a larger count to make a more confident statement about your lifetime or so. Okay, so that's why you will see in a counting experiment, people suppose you want to know how many counts you get per minute. Suppose you get how many counts you get in 1 minute. Suppose this is your question. Okay, And if you keep your stopwatch to set to only count the number of particles in precisely 1 minute, and you say that in 1 minute the number that comes out to that come out of this radioactive sample is basically say 2 to 3. You get sometimes at 2 counts, sometimes at 0 counts, sometimes at 5 counts. Okay, so you see this number is really low, and that translates into a larger relative error. So what you do in this case is that, suppose you say, you do not ask how many counts you get in 1 minute. So if you want to know that, then what you do, that you actually do the experiment, that how many counts you get in say 40 minutes. Okay, so you wait for 40 minutes. Okay, and then probably you get at an average of say 90 counts. Okay, and then your relative error goes down because of this 1 by square root of this thing. And then when you need to quote what is the number of counts you get per minute, you just divide this by 40. Okay, so it's whenever you are measuring something that follows a Poisson distribution, you should keep in mind that you keep your counts to have sufficiently high values so that you can give a more confident statement about your observations. Okay, and but so what so Poisson distribution is not only applicable in this particular counting experiment. Usually in other counting experiments also, whenever these counts are involved, you usually have this scenario that you have large number of sample spaces, and probability of success is small, and you can usually approximately assume that it will more or less follow Poisson distribution. One typical example will be in social science also. Suppose you need to check the number of births in every 3 days, okay, in a country like India. Okay, that will also follow a Poisson distribution. So you just count the number of hospitals. The number of hospitals is really large. Okay, so not this large, but fairly large. So the number of kind of trials is also large, and the probability that on a given day one hospital will give a birth to a child, or there is one pregnant woman admitted to that hospital, is fairly low, that in a particular hospital. So p is small, but the product is large. So if you kind of find out a distribution that the number of babies born in a certain interval of time, and that will follow a Poisson distribution also. It is expected to follow a Poisson distribution also, that is constant then. So I think I will end today's lecture here, and I can now take questions if you have any. All right, I don't see a question, so I assume that everything is fine. In that case, I will stop recording now, and we will meet again on Monday at scheduled time. Okay, the scheduled time is from 2 to 3, so I will see you then.